Thank you everyone for coming to my talk. So I'm going to tell you about my research on StickOn electricity meters for building submetering. And these are built using all off-the-shelf components, in case you're not familiar with the acronym COTS. So this is a collaboration between UC Berkeley and Lawrence Berkeley National Lab. So first, I'd like to motivate this work. There's been research that has shown we can save 10 to 30% of our electricity usage with submetering and subsequent follow-up action. But the question is, how do we get this data? So on the bottom of the slide, you can see what a commercially available solution to submeter a building looks like today. And the way this works is as follows. A current transformer is clipped around the wire coming from every circuit breaker, and an additional wire goes to every circuit breaker for a voltage measurement. And as you can see here, it's not a very streamlined solution. There are a lot of wires. It's a real rat's nest. And one of the other major downfalls to a solution like this is that an electrician is required for the installation. So an electrician has to come in. They have to open up and get inside of the panel and perform the hot work to install the current and voltage connections. And they also might have to install enclosures or conduit external to the circuit breaker panel for the signal leads. And so this electrician cost ends up being a very large portion of the total installation cost. And for example, a mid-size, mid-life building could cost up to $100,000 for three-phase submetering. And so this large initial investment leads to a long payback period, which could be in excess of 10 years. So it's not a very lucrative investment for building owners. And so how are we going to solve this problem? We're proposing to use StickOn electricity meters. So now you see this acronym SEM. I'm going to use that through the rest of the talk, and that means StickOn electricity meter, not scanning electron microscope. And so these SEM sensors, excuse me, so they are non-contact based sensors that measure both voltage and current, so they can calculate real power. And these sensors are installed on the external circuit breaker, on the external face of the circuit breaker. And so all these sensors are connected together with a wired bus. And this wired bus then connects to a panel base station, which transmits all the data out wirelessly. And on the right, you can see a mock-up of what we think this sensor would look like placed on a circuit breaker. And so through the combination of low-cost hardware and drastically reduced installation time, we believe that the overall system can be installed in a building for a much lower cost and time. So now I'd like to show you what two main types of circuit breakers look like internally. So on the left, you can see what is referred to as a thermal actuated circuit breaker. And the actuation method here is a bimetallic strip. So when the current through the circuit breaker gets large enough, the bimetallic strip heats up and it deflects enough to the point where it can trip the breaker and stop the current path. On the right, you see what is referred to as an EM actuated breaker. So this breaker has a solenoid inside, and it functions fundamentally different. So when the current through the breaker gets large enough, the magnetic field concentrated by the solenoid gets large enough, and eventually a Lorentz force is strong enough to pull in a lever and actuate the circuit breaker. So for clarity here, I've annotated where our SEM sensor would be placed on these breakers. And one more thing that I would like to point out here is that in the design of a non-contact based power meter for something like this, the EM actuated breaker is actually a lot easier. And that's because the solenoid in the breaker increases the magnetic field strength in that region by 10 to 20x. So the thermal actuated breaker is a lot harder. Unfortunately, what we've seen is that this type of circuit breaker is a lot more common. So that's the focus of our work, and all the data I present today is measured on a thermal actuated breaker such as this. So now I'd like to tell you the power sensing techniques we're using for our sensor. So we're sensing the circuit breaker's line voltage capacitively. So here I've highlighted a capacitance that is formed between the conductor in the circuit breaker and the SEM device itself. And a current is induced through this capacitance, which is proportional to the derivative of the line voltage on the circuit breaker. And so this current is then sensed by the SEM sensor using the analog front-end circuit you can see on this slide. And so it's sensed and amplified, and then an ADC digitizes the signal for subsequent processing. And to sense the current through the circuit breaker, we are monitoring the magnetic field. So here you can see excuse me. Here you can see the analog front end we're using to sense the current. So there's a Hall effect sensor, a few analog filters, a high gain instrumentation amplifier, and again, the signal is digitized by an ADC. So now that we have the voltage and current signals, how do we calculate the power? So I previously mentioned that the sensed voltage signal is proportional to the derivative of the actual line voltage. So that ends up resulting in a minus 90 degrees phase shift on the sinusoid. So what we did is we built a PLL in software which tracks the phase of this voltage sense signal here, and then implements a positive 90 degree phase shift to account for the derivative. So the output of that is then multiplied by our current signal, and the result of the multiplication is then scaled by a factor K, which comes from a calibration, which I will discuss in more detail later. And then the output of the calibration block then is power in watts. So here are some more details about the prototype that we have built. At the top, you can see a block diagram of the system. And on the right side, you can see an image, a photo of our PCB prototype compared to a quarter. So on every SEM PCB, there's a Hall effect sensor, multiple amplifiers, and an MSP430. So the MSP430 samples the voltage and current signals at 960 hertz, and it also serves as a wired communication link to transmit the data to the wireless mode, which then sends the data out to a server nearby. And we're very excited to announce that green box is supposed to be over the green text. That the component cost is roughly $10 in only quantities of 25. And again, this is with components that are all available today. So it's pretty cheap even in small quantities. Okay, and on this plot, what we're looking at is the real power output of the SEM prototype versus a reference power meter for various resistive loads. So here you can see that the output of our sensor is very accurate in sensing power all the way down to below 10 watts. And this measurement was taken with 16x averaging for improved SNR. Okay, and I'd also like to show some example time domain waveforms from our sensor. So these measurements were taken with a triac dimmer load, and that triac dimmer leads to a very nonlinear current. So the trace in red is the current, and you can see that, like I said, it's very nonlinear. But due to our wide bandwidth signal path, we're able to successfully capture the nonlinearities of that current chopping there. And so here in green, you can see the measured dV/dt signal, as well as the phase-corrected synthesized voltage signal in blue. So in order to investigate the performance of this device in a real-world environment, we installed our SEM system on a residential dwelling's kitchen circuit. So on the left, you can see an image of the installation. So the SEM sensor is installed right here on this breaker, and the wireless mote is up here at the top of the panel. And so now I'd like to tell you how we calibrated the SEM device. So while the SEM was installed, we plugged in various known resistive loads to the kitchen circuit. We just plugged them right into the outlet in the kitchen. and we monitored the change in output on our SEM sensor. And so that enabled us to connect the dots between the output of our sensor and real power in watts. And then so that result is then fed back into the software basically as that calibration factor I mentioned earlier. And so this panel was also had a TED 5000 whole house power meter installed, and that served as a reference measurement for this work. So on the right, you can see both the output of our SEM sensor and the whole house power meter over a period of 8 hours. And I'd like to make note that again, the whole house power meter is measuring various other circuits that have other loads on them. So that's why the curves are offset by various amounts as time goes on. So what is important to note here is that our sensor tracks loads with non-unity power factor, such as refrigerator, microwave. And another thing that's pretty interesting we found from this data is that often the kitchen circuit's power usage is over 50% that of the whole house. So that was pretty interesting. Okay, so to wrap up, I'd like to give a summary of the performance in comparison to a similar work which was published here in 2011. So that work used the custom MEMS process for a current sensor. So this work is made using a standard PCB assembly and fabrication process, which is widely available worldwide. And our sensor has a wide bandwidth, and it can measure current, voltage, as well as real power, and it does so with a reasonable resolution. So in summary, we have demonstrated the feasibility of a low-cost, non-intrusive power metering device built using all off-the-shelf components. And since it's non-intrusive, this can be installed on the face of the circuit breaker panel, and therefore a costly electrician is not required. So this leads to roughly 10x lower install cost and time compared to the commercially available solutions which I outlined at the beginning of the talk. So we hope that this will lead to more widespread deployment of systems like this, because detailed energy data, again, leads to significant energy savings. And I'd like to make some acknowledgments. First, Lawrence Berkeley National Lab for funding, and the co-authors on the paper who could not make it today. And that concludes my talk. Thank you very much.